In the vast expanse of our universe, astronomers continually make discoveries that challenge our understanding of stellar evolution and physics. One such recent discovery is a peculiar white dwarf star nicknamed Giannis. This celestial oddity has captured the attention of the scientific community due to its unprecedented two-faced nature, one side composed of hydrogen and the other of helium. This article delves into the details of this groundbreaking discovery, exploring its significance in the field of astrophysics and the potential explanations for this unusual phenomenon. Understanding white dwarfs. Before we dive into the unique characteristics of Giannis, it's crucial to understand what white dwarfs are and how they typically behave. What is a white dwarf? White dwarfs are the remnants of stars that have exhausted their nuclear fuel. These stellar corpses, typically about the size of Earth but with a mass closer to that of the Sun, represent the final evolutionary state for the majority of stars in our universe, including our Sun. Composition and structure. White dwarfs have some of the highest densities found in the universe, second only to neutron stars and black holes. This extreme density leads to some fascinating physical properties. Gravitational settling. The intense gravity of a white dwarf causes heavier elements to sink towards the center, while lighter elements float to the surface. Layered structure. Typically, white dwarfs have a layered structure with the heaviest elements at the core and progressively lighter elements towards the surface. Surface composition. The surface of most white dwarfs is composed of the lightest elements, primarily hydrogen and helium. The typical evolution of white dwarf surfaces. Under normal circumstances, the evolution of a white dwarf's surface composition follows a predictable pattern. Hydrogen-dominated phase. Initially, hydrogen, being the lightest element, floats on the outer surface of the star. Cooling process. As the white dwarf cools over billions of years, the hydrogen eventually sinks. Helium-dominated phase. Once the hydrogen sinks, helium becomes the dominant element on the surface. This transition from a hydrogen-dominated to a helium-dominated surface is a well-understood process in stellar evolution. However, the discovery of Giannis challenges this simple model. The discovery of Giannis, a stellar anomaly. Giannis, named after the Greek basketball player Giannis Antetokounmpo, known as the Greek Freak for his exceptional and unusual abilities on the court, is the first white dwarf ever observed with a clear dichotomy in its surface composition. Observational details. Astronomers using advanced spectroscopic techniques made this unprecedented discovery. Spectroscopy allows scientists to determine the chemical composition of distant stars by analyzing the light they emit. In the case of Giannis, the spectra revealed something never before seen in a white dwarf. Hydrogen-dominated hemisphere. One side of the star showed a spectrum consistent with a surface primarily composed of hydrogen. Helium-dominated hemisphere. The other side displayed a spectrum indicating a helium-dominated surface. This stark contrast between the two hemispheres of Giannis is what makes it truly unique in our current understanding of white dwarfs. The significance of the discovery. The observation of Giannis' two-faced nature is more than just an astronomical curiosity. It has significant implications for our understanding of stellar evolution and the physical processes at work in white dwarfs. Challenging existing models. The existence of Giannis challenges our current models of how white dwarfs evolve. The clear demarcation between hydrogen and helium-dominated regions suggests that the transition between these phases may not always be as smooth or uniform as previously thought. Insight into stellar physics. This discovery provides a unique opportunity to study the processes of element separation and mixing in extreme gravitational conditions. It may offer new insights into the behavior of matter under intense gravitational fields. Potential for new stellar classifications. If more stars like Giannis are discovered, it might lead to a new classification within the family of white dwarfs, expanding our understanding of the diversity of these stellar remnants. Hypotheses explaining Giannis' unique nature. Scientists have proposed two main hypotheses to explain the unusual two-faced composition of Giannis. Both of these center around the role of magnetic fields in shaping the star's surface composition. Hypothesis 1. Asymmetric magnetic field. The first hypothesis suggests that Giannis is surrounded by an asymmetric magnetic field. This uneven magnetic field could be preventing the mixing of elements on the more strongly magnetized side of the star. Mechanism. The stronger magnetic field on one side could create a barrier, preventing hydrogen from sinking or helium from rising to the surface. On the less magnetized side, the normal process of elements settling would continue, leading to a helium-dominated surface. Implications: if true, this would provide valuable insights into the role of magnetic fields in stellar evolution. It could also help explain other anomalies observed in some white dwarfs. Hypothesis 2: magnetic field affecting surface pressure. The second hypothesis proposes that the magnetic field is affecting the gas pressure at the star's surface, allowing hydrogen to pool in areas where the magnetic fields are strongest. Mechanism: magnetic fields can exert pressure on ionized gases, plasma. In regions of stronger magnetic fields, this additional pressure could counteract the gravitational settling of hydrogen. This would result in hydrogen remaining on the surface in magnetically strong regions, while sinking in areas with weaker fields. Implications: this hypothesis suggests a more dynamic interplay between magnetic fields and element distribution in white dwarfs. It could lead to new models of how magnetic fields shape the structure and evolution of these stars. Challenges in studying Giannis. While the discovery of Giannis is exciting, studying this unique star presents several challenges. Distance and brightness. Like many white dwarfs, Giannis is likely to be relatively dim and distant, making detailed observations challenging. This requires the use of powerful telescopes and sensitive instruments. Rotational period. Understanding how Giannis rotates is crucial for interpreting its two-faced nature. Determining the rotational period of a small, distant star is a complex task that requires prolonged observation. Magnetic field measurements. Directly measuring the magnetic field of a white dwarf is challenging. Scientists often rely on indirect methods, such as analyzing the Zeeman effect in spectral lines, which requires high-resolution spectroscopy. Implications for future research. The discovery of Giannis opens up several exciting avenues for future research in astrophysics. Search for similar objects. Astronomers will likely begin searching for other white dwarfs with similar characteristics. This could help determine whether Giannis is a unique anomaly or represents a new class of white dwarfs. Detailed modeling. Advanced computer models will be needed to simulate the physical conditions that could lead to Giannis' unique composition. This could involve complex magnetohydrodynamic simulations. Evolution over time. Long-term observations of Giannis could provide insights into how this unusual star evolves. Will the two-faced nature persist, or is it a temporary phase in the star's life? Improved observation techniques. The study of Giannis may drive the development of new observational techniques to better analyze the composition and magnetic fields of white dwarfs. Conclusion: the discovery of Giannis, the two-faced white dwarf, represents a significant milestone in our exploration of the universe. This unique star challenges our understanding of white dwarf evolution and offers a rare opportunity to study the complex interplay between gravity, magnetic fields, and element distribution in these dense stellar remnants. As astronomers continue to study Giannis and search for similar objects, we can expect new insights into the physics of white dwarfs and potentially a broader revision of our models of stellar evolution. The existence of this celestial oddity reminds us that the universe is often stranger and more complex than we imagine, continually pushing the boundaries of our scientific understanding. The story of Giannis also highlights the importance of continued astronomical observations and the development of advanced observational techniques. It demonstrates that even in well-studied areas of astronomy, there are still surprising discoveries to be made. As we look to the future, the study of unusual objects like Giannis will undoubtedly play a crucial role in advancing our knowledge of the cosmos. Each such discovery brings us one step closer to unraveling the mysteries of the universe and our place within it.